Have you ever felt a static shock after walking across a carpeted room and touching a doorknob? Or seen your hair stand on end after rubbing a balloon on your head? These everyday experiences are driven by an invisible force known as electrostatics. Electrostatics is the study of stationary electric charges and the forces they exert on each other. Our exploration begins with the concept of electric charge, the fundamental property of matter that gives rise to electrostatic forces. At the heart of electrostatics lies the concept of electric charge, a fundamental property of matter that governs how particles interact with each other through electric forces. There are two types of electric charge, positive and negative. Objects with the same type of charge repel each other, while objects with opposite charges attract. The unit of electric charge is the coulomb, named after the French physicist Charles-Augustin de Coulomb. For perspective, a single lightning bolt carries only about 15 coulombs of charge. The principle of charge conservation states that the total electric charge in an isolated system remains constant. In the 18th century, French physicist Charles-Augustin de Coulomb conducted groundbreaking experiments to quantify the force between charged objects. Coulomb's law states that the magnitude of the electrostatic force between two-point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. Mathematically, Coulomb's law can be expressed as F equals K times the absolute value of Q1 times Q2 divided by ER squared. This equation reveals that doubling the charge of one object doubles the electrostatic force between them. Doubling the distance between two charges reduces the electrostatic force to 1/4 of its original value. Coulomb's law is a fundamental principle in electrostatics, allowing us to calculate the force between any two-point charges. Imagine a single stationary charged object, such as a positively charged sphere. This charged object creates an invisible region of influence around it, called an electric field. The electric field is a vector field, meaning that it has both magnitude and direction at every point in space. The magnitude of the electric field at a particular point is a measure of the force that a positive test charge would experience if placed at that point. The direction of the electric field is defined as the direction of the force that a positive test charge would experience. The electric field provides us with a powerful tool for understanding how charges interact at a distance. While the concept of an electric field provides us with a powerful tool for understanding the influence of charges, it can be quite challenging to visualize this abstract concept. To tackle this, we use electric field lines, a visual representation of electric fields that helps us understand their properties and behavior. Electric field lines are imaginary lines drawn in space such that the tangent to a field line at any point gives the direction of the electric field at that point. By convention, electric field lines originate from positive charges and terminate on negative charges. The density of electric field lines is proportional to the strength of the electric field. This visual representation allows us to quickly assess the relative strength of the electric field at different points in space. Just as objects in a gravitational field possess gravitational potential energy due to their position relative to a massive object, charged objects in an electric field possess electric potential energy due to their position relative to other charges. Electric potential energy represents the stored energy that a charged object has by virtue of its position within an electric field. To understand electric potential energy, imagine moving a positive test charge against the electric field of a positive source charge. This movement requires work because we are pushing the test charge against the repulsive force exerted by the source charge. The work done in moving the test charge is stored as electric potential energy in the system. The higher we move the test charge against the electric field, the greater the electric potential energy it acquires. While electric potential energy provides us with a measure of the energy associated with a charged object's position in an electric field, it depends on the charge of the object itself. To obtain a quantity that is independent of the test charge, we introduce the concept of electric potential, often referred to as voltage. Electric potential, denoted by V, is defined as the electric potential energy U per unit charge QV equals UQ. The electric potential at a point in an electric field represents the potential energy that a unit positive charge would have if placed at that point. Equipotential surfaces are always perpendicular to electric field lines, ensuring that no component of the electric field is parallel to an equipotential surface. The concept of electric potential is crucial for understanding the behavior of charges in electric circuits. Gauss's law provides us with a powerful tool for analyzing continuous charge distributions, relating the distribution of electric charge to the resulting electric field. Gauss's law states that the total electric flux through any closed surface is proportional to the total charge enclosed within that surface. Electric flux, denoted by PHE, can be thought of as a measure of the number of electric field lines passing through a given surface. Mathematically, Gauss's law is expressed as phi equals sign EDA equals sign quench EO. To apply Gauss's law, we typically choose a closed surface, known as a Gaussian surface, that simplifies the calculation of the electric flux. For highly symmetric charge distributions, such as a uniformly charged sphere or an infinitely long charged rod, we can choose Gaussian surfaces that exploit this symmetry. Gauss's law is one of the four fundamental equations of electromagnetism, known as Maxwell's equations. The principles of electrostatics extend far beyond the realm of theoretical physics, finding widespread applications in various technological advancements that shape our modern world. One of the most ubiquitous applications of electrostatics is in xerography, the technology behind photocopiers and laser printers. The process begins with a photoconductive drum, a cylinder coated with a material that becomes conductive when exposed to light. Toner particles, which are charged, are then attracted to the remaining charged areas on the drum. Finally, the toner image is transferred to a sheet of paper and fused using heat, creating a permanent copy. Electrostatic forces are also harnessed in various other applications, including electrostatic painting and electrosurgery. From the seemingly simple act of rubbing a balloon on our hair to the complex workings of electronic devices, electrostatics permeates our world, shaping our understanding of the universe and enabling countless technological marvels. By unraveling the mysteries of electric charge, Coulomb's law, electric fields, and Gauss's law, we have gained a deeper appreciation for this fundamental force of nature. We explored the concept of electric charge, the fundamental property of matter that gives rise to electrostatic forces. Moving beyond individual charges, we ventured into the realm of electric fields, invisible regions of influence surrounding any charged object. Visualizing these fields using field lines provided us with a powerful tool for understanding how charges interact at a distance. Finally, we explored the myriad applications of electrostatics, witnessing how this fundamental force underpins technologies that shape our modern world. Our journey into the world of electrostatics has provided us with a solid foundation for understanding the behavior of stationary charges and the forces they exert on each other. However, the story of electricity and magnetism doesn't end there. Electrostatics is just one piece of a much larger and more fascinating puzzle: electromagnetism. Electromagnetism unifies electricity and magnetism, revealing them as two sides of the same fundamental force. While electrostatics deals with stationary charges, electromagnetism encompasses moving charges and their interactions with magnetic fields. The interplay between electricity and magnetism gives rise to a plethora of fascinating phenomena, from the generation of electromagnetic waves to the operation of electric motors and generators.